So question 17 is a motion graph, and it's a speed time graph. We're given some data in the question, which we'll go through in a moment, but we can see that we have a train starting from rest. It accelerates to a maximum speed, then it decelerates back to rest again. And we are asked to find the speed of the train at point B in terms of t. So I'm going to write down what we know. So the first thing we do is we always write down what we know. We know that it starts from rest. So I'm going to write u equals 0. We know it accelerates at 0.20 meters per second squared. And we know that the total distance, the area under the graph, is 1800. Okay. We also know that the time it takes to go from A to B is 0.80 t, where t is the whole time. So we are asked to calculate v. So we write down what we know to this point, between here and here. We write down what we don't know, and then we find a relevant formula. So if we look in A1 kinematics, we've got the kinematics equations, and we are trying to find v. We have uat, so I am going to use this formula. I don't need to rearrange because I'm trying to find v, and v is already the subject, so I'm going to put u is 0 plus 0.20 multiplied by 0.80 t, and if I multiply those together I get 0.16 t. So that is the speed of the train at point B. For part B, we're asked to calculate the total time for the journey. So here we have two triangles. Okay, so let me just rub this out. We have two triangles which would calculate the distance. So we've got the distance is the area under the graph. So we've got kind of distance 1, and then we've got a distance at this new acceleration, and then if we add them together we'll get the total distance. So we've got two triangles, and so it's half base times height. So for S1, so for distance 1, it's half base times height. So half times the base is 0.8 t, and we're going to multiply that by the height. Now the height of it is the speed that we've just calculated. So we're going to multiply that by that. Okay. And we are then going to add S2, half base times height. Now the base is this distance. So it's 1t minus 0.8t, which is 0.2t, multiplied by the height, which again is 0.16t. Okay, so if we take these two and add them together, we get a total of 0.08t squared. We know that the total distance, so that's the total distance, and we know that that equals 1,800 meters because it's given here. So we know that these two equal 1,800 meters, so I'm going to put 1,800 meters equals this, and we rearrange. For t squared we get 22,500, therefore the square root is 150 seconds. Question 18, we have a block on top of another block. We're told there's no friction between the block and the table. So there is no friction between there, it's frictionless. However, there is friction between the 15 and 45 kilogram one. We know that the coefficient of static friction between the block and the object is 0.6. So we have a static friction here. Now, when this block is accelerated by applying a resultant force, so when there's a resultant force, this is going to accelerate. Now, it says that they do not move relative to each other. Okay, so whatever acceleration this one has, the smaller block also has the same acceleration. Otherwise, it would move relative to it. Okay, so if this has an acceleration, that means this one has an acceleration. Now, the reason this one accelerates with it is because of the resultant force, which is the static friction. So the direction of the force that accelerates the 15 kilogram object is static friction to the right. Okay. So only static friction pushes the top block forward. So we're looking for static friction plus right. Now for B, we're asked for the largest magnitude of the force for which the block and the object do not move relative to each other. So what we're looking for is the maximum friction. So at the limit where friction is at its maximum, that is where the blocks will remain stationary to each other. So let's look at what's going on. So we have the top block and we have the bottom block. And let's look at them individually and then we'll bring them together to see what's happening. So the top block has a friction, has a force. I'm going to call that little f. So the top block has a force that is equal to ma. I'm going to call it mass 1 and mass 2. Okay. The bottom block is subjected to a force, but then we have to take away the frictional force from the top block that's pulling it back. So that is going to be equal to its mass multiplied by the same acceleration. Now, if I want to create one formula out of these, I'm going to say force F, which is causing the acceleration, minus little f, and so I'm going to substitute this in, equals m2a. Therefore, the force is m1a plus m2a. What you could do is put them into brackets, but you don't need to. All right, so we have an expression for capital F. Now, in order to calculate the overall force, we need to know the two masses, which we're given. So we're given that, and the acceleration. We don't have the acceleration, but we can find it. So the maximum acceleration will occur at the point where the static friction is maximum. So if we look at our friction diagram, it goes something like this. Yeah, and we see that you've got your maximum static friction here, and then kind of the dynamic friction, dynamic friction kicks in as you keep increasing. So we're looking for this value. So we know that the acceleration will be maximum when you've got a maximum friction. Now, in order to calculate the maximum static friction, it's mu s multiplied by the normal. Now, the friction is on mass 1. So this is for mass 1. So the maximum static friction, this is to calculate A. Okay, so we're trying to calculate A. We can then sub in the masses and find the overall force. So we've got 0.60 as the static friction coefficient, multiplied by 15 kilograms multiplied by gravitational field strength, and that equals 88.2 newtons. We know that F equals ma, so if I take this force and divide it by the mass which it's on, which is the 15, divided by 15, we will get the acceleration of mass 1, and we know that that equals mass 2 as well. So our final step to find F, we have this expression m1 plus m2 A. Therefore, m1 plus m2 is 60 kilograms multiplied by 5.88, which gives a final answer of 353. If you were looking for the correct sig figs, it would be 2 sig figs. Okay. This question is talking about buoyancy and Stokes's law. We have a bubble of gas rising at constant speed. I'm going to highlight rising as well. Filled in a container of liquid. So I've got a vessel of liquid and I have a bubble. It's rising at a constant speed. So there is no acceleration. That's important. So before we even look at the question, I'm just going to draw the forces on it. Now, if it's rising, then the upthrust is equal and opposite, because the acceleration is 0, to the drag. Now the drag is actually downwards because the motion is upwards. So these are equal and opposite. Let me do a slightly better scale. Okay, so our first step is to note buoyancy equals drag in the opposite directions. So show that the speed v of the bubble can be estimated as that expression. So the first thing I'm going to do is look in the formula booklet, and I'm going to write down the two formulae that we know. So we know that density times volume times g, that's our buoyancy from the data booklet, and then we've got our Stokes's law drag there. Okay. Now we are asked to rearrange for an expression for v. So I'm going to do that. So I'm going to put this, and then I'm going to divide both sides by 6 pi r viscosity, and then I've got an expression for v. Now this doesn't quite look like I was hoping for. So we need to see what we need to remove. So in our given expression, we have density, we have g, we have viscosity. We don't have volume and radius. So we need to remove those, and we can see that we need to represent the volume and radius in terms of radius only. So what that means is I need to put the volume in terms of r. Now they've done a capital R, but don't worry. But we are looking to remove the volume, because that isn't in what we're trying to find, and put it in terms of r. So I need an expression for volume in terms of r. Now I know that this is a sphere. We're told it's a sphere. because it is a bubble, and I know that volume is 4/3 pi r cubed. So now I'm going to go ahead and sub that in. So I've got density times 4/3 pi r cubed g over 6 pi r viscosity. So I'm going to cancel these. I'm going to cancel the pi's. And I've got 4/3 over 6, which is 4/18. And so I can go again, 2/9. Sorry, I'm just going to go down here. So I'm just going to write this out again so it's a bit neater. So I've got density times 2 times r squared times g over 9 nu. And it just so happens that that is the answer. Okay. For this question, you need to substitute the numbers you're given into the formula that you have derived. Okay, so I'm just going to write that out one more time. So I'll write it like they've written it, 2r squared rho g over 9 viscosity. And I'm going to put in the numbers. So I've got 2 times the radius. The radius is 0.45 millimeters. So it's 0.45 into meters squared times by the density. Now that's already in SI units, so that's good. Multiplied by G, 9.8. We're going to divide that by 9 multiplied by the viscosity, which is what we're trying to find. Sorry. And we know that the velocity is 18 centimeters per second, so I'm going to divide that by 100 to get it into meters. Now I'm going to rearrange that, and I get 2 times 0.45 divided by 1,000 all squared, times by 1,300 times by 9.8 divided by 9 times 18 over 100, and I get a value of 0.0032 Pascal seconds. Okay. Question 20 is a projectiles question. So I'm back to my kinematics equations from A1. 2 players are playing table tennis. Player A hits the ball at a height of 0.24 meters above the edge of the table, measured from the top of the table to the bottom of the ball. The initial speed is 12 meters per second horizontally. Assume air resistance is negligible. The ball bounces and then reaches a peak height of 0.18 meters above the table with a horizontal speed of 10.5 meters per second. The mass of the ball is 2.7 grams. Now, just whilst I'm going through the numbers, I don't know if I'll need it, but I am aware that we will need to convert this. So something I like to do is just see where the conversions might be whilst I'm reading the question, because once you get stuck into the calculations, it's very easy to miss a conversion. So just whilst it's fresh in your mind and you're reading through the numbers and you're highlighting what you might need, you could always write down the word conversion. So you could do that here, for example, convert, and it's just a heads up. Or you could always highlight in an exam, you could always highlight the words that you need to pay extra attention to. Okay, so show that the time taken for the ball to reach the surface of the table is about 0.2 seconds. So we are looking for the the time taken for the ball to fall that distance. Now, the only reason the ball is falling is because of the acceleration due to gravity. So, if I'm trying to find a time, what I'm going to do is I'm going to write SUVAT. I'm going to write my horizontal and my vertical. Let's see what we've got. So, I'm trying to find time. I know that acceleration horizontally is 0. I know that vertically it's 9.8. I know that the vertical distance it falls is 0.24 meters. I do not know this distance. I don't know the range whilst it falls, so I don't know that. I know that the initial horizontal speed is 12, and at the point where it strikes, it's still 12. I know that the initial vertical velocity is 0 because it only has horizontal velocity, and the final velocity I don't know. So this is what I've got. So I am trying to find t. So if I'm trying to find t, I need a kinematics equation, and I have the options of these kinematics. I'm just going to write down all the kinematics equations that include t, and then let's see which ones we can use. Okay, so these are my options. Now, if I want to use this one, I'm looking at the horizontal. Do I have S? No. So if I'm trying to find t, I already know that that's an unknown. Let me just highlight that. Oh, sorry. I'm just going to highlight that. So this is sorry. Sorry, bear with me. So this is an unknown. All right, so we don't have that. So we have to have all the other symbols. Okay, that's what I'm going for. So let's see, one of them is going to work. So if I'm trying to use this one, if I look at the horizontal, I don't have S. So I can't use this one for horizontal. Can I use it for vertical? No, because I don't have V. So I can't use this one. Let's go to the next one. V equals U plus AT. Let's have a look at the horizontal. Do I have the V? Yes. Do I have the U? Yes. Do I have the A? Yes, but it's 0. Now, if it's 0, anything multiplied by 0 is 0. So actually, I can't use this one in the horizontal because I would end up with 0 times t. If I'm trying to find t, it's going to drop out to kind of 0. So I can't use it in the horizontal. Can I use it in the vertical? So my V is, I don't know. So I can't use this. So I can't use this one either, automatically. Let's have a look at this one. S, well, I know I don't have that, so I can't use that in the horizontal. Can I use it in the vertical? So I've got S, yes. U, I've got, it would drop the T, but we're still okay. We might be able to use it here. So that would drop to 0, okay? However, can we use it here? Half times 9.8 times t squared. Yes, I have that. I'm trying to find that. I can use this formula. So S equals ut plus half at squared. So I know that 0.24 meters of vertical height equals 0t plus half times 9.8 times t squared. So 0.24 equals 4.9 t squared. Therefore, t equals 0.22 seconds. We're asked to show that. So I'm going to go back. Does it look very close to 0.2? Yes. There we go. I'm not going to write it equals 0.2 because it doesn't. It equals 0.22, etc. Okay, so I need to include an additional sig fig. So if it's a show that question, you always need more sig figs. Otherwise, you won't get the mark. Okay, so you need to show more sig figs. Sketch on the graph the variation with time of the vertical component. Sorry, graph shows the variation with time of the vertical velocity until it reaches the table surface. Take g to be 10. So we've got a velocity time graph and we need to sketch. So we know that in a velocity time graph, the aspects of a velocity time graph are the distance is the area under the line. And we also know that the acceleration is the gradient. Now we're given the gradient to be 10. So I am looking at a gradient of 10. In other words, a 10 to 1 ratio. So V to T is 10 to 1. So I know I'm going to have a gradient of 10. So let's have a look at that. So it's a 10 to 1. So if I go across point 1, I need to go up 0.1 times 10, which is 1. So I'm going to put a dot there. If I go across point 2, I need to go 10 times bigger than point 2 up, which takes me to 2. So I'm going to have a line that goes through these crosses. How far do I need to go? Do I need to go all the way through, or I need to find until it reaches the table surface? So let me just remind myself of the time when it hits the table surface. Show that the time for the ball to reach the table surface is 0.2. So you can either go to 0.2, or if you manage to get it to more significant figures, you can use that as well. So it doesn't matter. But we're either looking to stop at 0.2 or 0.22. So I'm going to stop at 0.2, but you don't have to. You could stop at 0.22. So with a ruler, which I can't do digitally, we're going to do that. Okay. For this question, we're asked to show that the ball will go over the net. So we have a diagram here and we're given additional information. So we are told that the table length is 2.74 meters and the net has a height of 15 centimeters. So I'm just going to go up here. We're told that the table is 2.74 meters and the net is halfway across. So the range that the ball will have travelled when it goes past the net, either into the net or above the net, is 1.37. We also get told that the height of the net is 15 centimetres. So I'm going to put that in metres. That's a conversion. Okay, I'm just going to write convert. Show the ball will go over the net. In other words, we need to show that when it's travelled at this distance, at this speed, the loss of height due to gravity will be less than the height of the net. Okay, so the first thing we need to do is write down what we know. So we said that is now 1.37. We know that, we know the initial speed is 12 and it doesn't change because there's no air resistance, therefore there's no acceleration. We know that in the vertical it's going to drop a certain height, so we don't know that. We don't know that. We know the initial speed is 0. We don't know the final speed. We know that it's accelerating due to gravity at 9.8. Right, so we are trying to find this. That's our ultimate goal. we need to know the change in height. So we need to know the change in height from 0.24. So 0.24 to what? So we need to know the change in height and then see if 0.24 minus the change in height is bigger than 0.15. If it only drops kind of 5 centimeters, it would take it to 19 centimeters, which means it would clear. If it falls 10 centimeters, that would mean it's only got 0.14 left, which means it will hit the net. So we need to find the drop, the vertical drop, the vertical distance traveled by the time it reaches the net. So this is what we're looking for, but we don't have the time. We need the time, because if we go back to our kinematics equations here, for every single one of these, if we're trying to find the height, we need to have the time. So we can't find it through here, so we're going to have to, step 1, find the time horizontally, know that that's going to be the same, and then step 2 is going to be to find the distance. So step 1, we need to find the time it takes to get in line with the net. Okay, so we're going to go horizontal. So we've got S, U, V, and T. So I am going to use let's use S equals VT. So distance equals speed times time. 1.37 divided by speed equals the time, which is 0.114 seconds. I'm now going to put that in. So at 0.114 seconds, it passes the position of the net. So 0.114. I'm now going to put that into my vertical. So I'm trying to find S. Vertical. So S equals UT plus half AT squared. I could use that. So the distance travelled vertically equals 0 plus half times 9.8 times 0.114 squared. And so the drop is 0.065 meters. So it's dropped 6.5 centimeters. So that's looking good. It's looking promising. So that is 6.5 centimeters. So we're starting. So we're starting up here at 0.24. We're dropping that amount, which means we have reached above the ground this distance. That minus that equals that. Now the net is only that distance, so it clears it by 2.5 centimeters. So let's just show that. The height minus the fall is that. So that's the height above the ground, and it's greater than the net. So yes, will clear. (21) We have a ball of mass 2.7 grams. It's released from rest from a height of 28 meters above the horizontal ground. Show that, more sig figs. In absence of air resistance, the ball impacts the ground with a speed of about 23 meters per second. Okay, just spotted grams. Don't know if I need it, but I'm just going to put a note to myself, convert. Don't like grams, want kilograms. Okay, so we're trying to find V. So we know that at the top it's at rest. We know the distance fallen is 28, and we're trying to find v. We don't know the time, but we do know acceleration due to gravity is 9.8, and there is no air resistance, so there is no change to that value. So we have, let's do our thing. We've only got vertical values, so I'm going to write suvat. S is 28 meters. U, it will start from rest. V is what we're trying to find, 9.8. So this is all the stuff we've got. We don't have T. So now I'm going to look at my kinematics formulae, which I'm starting to get used to because I'm using them a lot. And I am going to use V squared equals U squared plus 2AS. So V squared equals 0 squared plus 2 times 28 times 9.8. Sorry, they should be the other way around. 2 times A times 28. Now, if I work that through, I get V squared equals 548.8. So V is the square root of 548.8, which is 23. Oh, looking good. More sig figs. An air resistance force F acts on the ball. So now we're introducing air resistance. Okay, so this 23.4, I'm just going to say without drag. Okay, so this question here is no drag. This question, yes, drag. Okay, I'm highlighting that for you because a number of people used the no drag part of this question for the drag part of the question. Okay, so I'll come back to that in a minute, but just note that A is no drag, B is now introduced drag, and C leads on from B. Okay, and I'll show you why. So, determine the unit of K in terms of fundamental units. So, fundamental units are SI units. So, we are told that formula. We are looking for K. So, the first thing I'm going to do is rearrange for K. So, I'm going to divide both sides by V squared. Okay, so F over V squared is equal to K. And so if we can find the units of F over V squared, we can find the unit of V. So we know that this is newtons divided by meters per second squared. So we've got meters per second squared. So it becomes meters, actually let me just leave it like that. Now, newtons isn't an SI unit, so we need to convert newtons into SI. So I'm going to go to a different formula. The first formula I can think of is F equals ma. It's a very common formula. And so I know that newtons comes from mass times acceleration. So let me write out the units for these. So kilograms multiplied by meters per second squared. Kilograms is SI. Meters, SI. Seconds, SI. So, if I can represent newtons in kilograms meters per second squared, and then divide it by meters per second all squared, I will be able to get it into SI. So, let me multiply out this bracket. So that leads to kilograms meters per second squared divided by, multiply out the bracket, meters squared per second squared. Cancel, cancel. Meters divided by meters squared goes to that. So I'm left with kilograms per metre. Put it into IB notation, and we get that. Describe how the ball reaches terminal speed, terminal velocity. So, if something has terminal speed, it means there is no acceleration. So, what's happening is, initially, there is a resultant force, which equals ma, and that comes from the acceleration due to gravity. However, if that acceleration drops to 0, there must be an equal and opposite force. So an equal and opposite force, okay, so when A is 0, F is 0, therefore there must be a build-up of an opposing force. And so we need to talk about that. So we're going to talk about this build-up of opposing force. So if I've got a ball and it is accelerating to the ground by weight, initially that is my resultant force. So that is my resultant force here, where the acceleration is gravity. So like that, okay? Over time, the resultant force is balanced out by an upwards force, which is drag. When these are equal and opposite, the resultant force becomes 0, therefore the acceleration is 0, therefore we've reached terminal velocity. So let me put that into words for you. As the ball speeds up, drag increases. So as the velocity increases, drag increases. Until it equals the magnitude of the weight. When they are equal, the resultant force is 0. The acceleration becomes 0, and therefore V is constant. Now this ball has now reached terminal velocity. We can see it's reached terminal velocity because it's a VT graph. So here is the acceleration, the gradient. We've got acceleration here. Acceleration is always the gradient. Now we've got a steep gradient here, so the acceleration down is large. The acceleration is getting small, and then finally the gradient of a horizontal line is 0. So the horizontal line becomes a gradient of 0, the acceleration becomes 0. So we have this build-up of drag, which is balancing out against the weight. Now this graph means there is drag. Drag is present. So this leads on from B, where drag is present. It is not A. Now some people, when they were trying to find the speed for this question, they were using the 23 that they'd found previously, but that was when there was no drag. You cannot use that, okay? State the value of the area under the curve. So the area under the curve of a speed time graph is distance travelled, displacement. The distance travelled for the ball from the instant it is released to the ground is 28 meters. So we know the value of the area of the curve is 28 meters. Because it's state, you didn't need to do anything more than that. Determine K. Now if I go back to this formula, I'm going to have to go back up the page. F equals kv squared. I'm going to note that down. Now, I know that F is air resistance. So air resistance is the drag force. Okay. So at terminal velocity, the drag force is equal and opposite to the weight. So the drag force is equal to mg. This is where that mass that I need to convert will come in. So I'm now going to put that into my formula. So the weight, which is equal in magnitude to the drag, equals kv squared. So the weight was 2.7 grams divided by 1,000 to get in kilograms times 9.8 equals k times speed squared. So what I need to do is look at this graph and see what speed is occurring when there is zero acceleration. So there's acceleration here, so I need to keep increasing the line until the acceleration gets to zero. Here is terminal velocity. I'm now going to read that off the graph. Be careful. So we've got 8, 9, 10. Halfway between 9 and 10 is 9.5. That value is 9.5 meters per second. Take your time when you're reading graphs. They won't necessarily be an easy scale. So I'm going to say 9.5 squared. Therefore, if I rearrange for k, I get 2.9 times 10 to the minus 4. And what was the unit? Kilogram per meter. Kilogram per meter. Good. The ball rebounds from the ground with speed 7.8. The ball is in contact with the ground for time t. The average force is 1.1 newtons. Determine t. Now, there are two ways of doing this. The first one's with momentum, which we had not taught you at the time. The second one is with Newton's second law formula. So, so there's two ways of doing this. You could either do it through impulse, which we had not taught you. Okay, so impulse is force times time, and that equals the change in momentum. We had not taught you that at the time. It's still possible to calculate this by looking at those symbols in another way. So we do know Newton's second law. We've been using that throughout the test. F equals ma. We are trying to find t. Now, t is hidden within one of these symbols. It's hidden within acceleration. We know that acceleration is the change in velocity divided by the time t. So I'm going to rewrite this formula, but subbing, is that the word you say? Substituting the acceleration for v minus u over t. Okay, let's see what I've got. So I'm trying to find t. Let's just check I've got everything else. T. So we're told the resultant force is 1.1. Sorry, I should have said resultant force is F equals ma. Resultant force is mv minus u over t. We know the mass. I'm not going to keep writing 2.7 over 1,000. I'm going to do it now in standard form. Let me remind myself what's going on. So we've got, so I'm just going to pause it just so I can check all my numbers. One sec. Yeah, okay. So the initial speed at which it strikes the ground is 9.5. So we've got this idea. Let me just draw it. It strikes the ground with a speed of 9.4, or velocity. Sorry, these are velocities. Okay, so direction matters. So we've got it initial velocity of 9.5. It then rebounds with a speed of 7.8. However, for acceleration, we're looking at velocity. So because this is in a different direction, I'm going to say this one is positive and that one's negative. Let's put those in. So 9.5 positive and minus 7.8. And now we just have t, which is unknown. So let's rearrange for t first of all. So I'm going to multiply both sides by t. Then I'm going to divide both sides by resultant force. Cancel. Cancel. Okay, so time is 2.7 times 10 to the minus 3 kilograms multiplied by the brackets of minus 7.8 minus 9.5 divided by 1.1. And I get a value of 0.042 seconds. The final question is about a box that's being pulled up a ramp inclined at 30 degrees. The string passes over a pulley on a frictionless axle, but friction acts between the base of the box and the ramp. Air resistance is negligible. The load has a mass of 3.5. I'm going to write down what we know just as we read through it. It's initially a height of 0.5 meters above the floor. The mass of the box, so let's say load, yeah, and then the mass of the box is 1.5 kilograms. The load is released and accelerates downwards at 2.4 meters per second squared. Show that the speed of the load when it hits the floor is 2.1 meters per second. Okay, so we're trying to find V. So we need more sig figs. All right, we're trying to find V. And I'm just looking, I've got A. I know the initial velocity of this is 0, and I know that the distance travelled is 0.95. So let me just look at this. I've got S, I know U, I'm trying to find V, I know A, I don't know T. But I've got enough for V squared equals U squared plus 2AS. Now this is a classic example of where you're given way more information than you need for a certain part of a question. Now in reality, this was a 2-mark question for this test. This came from a much longer question, which was worth about 11 or 12 marks. And it was talking about other factors like energy conversion and frictional forces and things like that. However, this was the initial part of that question. And so you don't need to refer to all of the different quantities. In fact, you mustn't get caught up with all of the different quantities. Just pick out what you know and what you need. So I'm trying to find V squared. I'm not going to get caught up in all the other values. And so I've got 2 times 2.4 times 0.95. So my v squared is 4.56. So v is square root of 4.56. So v is 2.14 dot 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 dot. Is it similar to 2.1? Yes. Is it more sig figs? Yes.